So this is a demonstration to show Lenz's law. So here I have two rings. They are made out of aluminum. On this one, I think you can see there's a gap. There's a gap there. So it's not a continuous ring. But over here, that's a continuous ring. So this is a closed ring. This one is an open ring. And what I'm going to do is that I'm going to bring a strong neodymium magnet towards the open ring, and you can see nothing is happening. But now I'm going to bring the strong magnet closer to the closed ring, and let's see what's going to happen. Can you see? I'm not touching it, but it's moving. So what's going on here? So this strong magnet, it has a magnetic field. And when I'm bringing that magnet closer and into this ring, the magnetic field across the closed ring, it's going to change. As a result, there's an induced current that is going around this conducting path. It's a closed ring. Aluminum is a very good conductor. So there's a induced electric current, induced voltage going through this path. And that itself is going to create a magnetic field that is going to oppose this. That is going to oppose this increasing magnetic field, which is external. Okay, so then since it's opposing, it's going to create the same magnetic pole. Let's say this is a south pole. Then the closed ring will create an induced magnetic field with a south pole. So that's why it's like repelling. If it's a north pole, then it will induce a magnetic field that has a north pole. So it's going to get deflected like a repulsive force. So this is a very nice demonstration for the Lenz's law, and you can see the open circle, the ring, there's nothing there. There's no induced current because there's a discontinuity. But here you can definitely see like motion. So that's because like poles, they repel.